This is a video for day 16 of Calc AB, more intermediate value theorem and trig limits day 1. Okay, so yesterday we talked about intermediate value theorem, and let's talk about that really quick over here. That's the stuff in this section that I wanted to remind you of. So remember what the intermediate value theorem says. That says if you have a function that's continuous on the closed interval a to b, so I have some x value a to b, got some endpoint there, some endpoint there, and I'm continuous. So I have some function that connects the dots there without lifting my pen. K has to be some value between those endpoints. So f of a, f of b, k is some value in the middle there. If that's all true, then there has to be some x value that we're calling c between a and b, such that the function evaluated at that point equals that k value. If you think about it, it makes sense, I hope. Now this is fancy math notation. Backwards e means then there exists. So there exists a c, which is an element, so essentially that's in that interval ab, such that f of c equals k. Okay, so let's say this was my question. F of x equals negative radical 100 minus x squared on the interval 0, 8. Is it continuous? Well, on 0, 8 it is. If I plug in 0, this is just radical 100. If I plug in 8, this is just 100 minus 64, still a positive value. If I picked a number like 12, I'd have a problem. We'd have a negative under a radical, but that's not this interval. So it is continuous on this interval, so that's good enough for me. Is this value of negative 8 between f of 0 and f of 8? If I plug in 0, I get negative radical 100, which would be negative 10. If I plug in 8, 64, 100 minus 64 is 36, so negative radical 36 is negative 6. And negative 8 sure is between negative 10 and negative 6, so the intermediate value theorem holds. That means I should be able to find a k value, or a c value, sorry, between 0 and 8, where f of c equals negative 8. So that's exactly what I did here. F of c equals k. Plug in c. So negative radical 100 minus c squared equals negative 8. You'll notice I canceled the negatives, and then squared both sides. Added the c over, subtracted the 64, we get 36 equals c squared. I had to take a square root, which gave me plus or minus, but why did I choose plus and not the minus? Remember, you got to be in that interval. So c equals 6 is between 0 and 8, negative 6 is not. Okay, second example. F of x equals 4 over x plus 2 on the interval negative 3 to 1, k equals 1/2. Is it continuous? Well, it's a rational, so there's a problem at negative 2. Negative 2 is an element of that interval. It's in that interval, so intermediate value theorem fails. There's nothing more you got to do. How about a piecewise function on the interval negative 2 to 3, where k equals 5? Is it continuous? Well, we've got to check. Individually, these are both continuous. The problem's going to occur where they break apart at 1. So the limit of 1 from the left, does that equal the limit of 1 from the right? Well, the limit of 1 from the left, I'd be using the top equation. If I plug 1 into x squared minus 4, we get 1 squared minus 4 is negative 3. 1 from the right would be using these values, bigger than 1, on the bottom equation. 1 minus 1 is 0. Uh-oh, left-hand, right-hand limit are not the same. So since the limit doesn't exist there, we know f isn't continuous at 1. And since 1's on that interval and it's not continuous, intermediate value theorem fails. And we're done. How about f of x equals 5 minus 2x squared on negative 3 to 1 with a k value of 0? It's just a parabola, so it's continuous. Check the endpoints. Negative 3, plug in negative 3, you get negative 13. Plug in 1, you get 3. K equals 0 is between those two endpoints. So the intermediate value theorem holds, so I should be able to find a c value that's equal to this k value. So I want f of c equal to k. Plug in c. 5 minus 2c squared equals 0. Solve for c. So I added 2c squared over, divided by 2, square rooted it. Square root of 5 halves is plus or minus 1.5811, blah, blah, blah. You have to be between negative 3 and 1, so positive 1.58 isn't in that, but negative 1.58 is. So it's negative radical 5 halves. Okay, so that was some quick examples of the intermediate value theorem. Again, go watch the video from yesterday if you want more explanation on that. Today we're going to talk about trig limits, and trig limits are going to be the next few days in class. So sometimes trig limits are pretty straightforward. The limit as x goes to 0 of sine of x is just 0. And you need to know what these graphs look like. So remember the sine graph. Sine's the one that starts at 0, increases, decreases, back to 0. And that obviously goes on. That's just one cycle. It goes on forever. So as I approach 0 from the left, and as I approach 0 from the right, the function's also approaching 0. We're going right into the origin there. So that's why the limit's 0. How about the limit as x goes to 0 of cosine? Well, that's 1, because cosine looks like this. Starts up at 1, ends at 1. So as I approach 0 from the left, I'm approaching 1. From the right, I'm approaching 1. So yeah, the limit of x goes to 0 of cosine x is 1. But what about the limit as x goes to 0 of sine x divided by x? So that's 0 over 0. That doesn't mean it does not exist. It certainly might exist. If you look at your graphing calculator, so what I did for this piece down here, I don't know, is there a calculator on here? Let's see. Oh yeah, that's a calculator. If I plug in sine of x over x, so if you want to grab your graphing calculator, no thanks. Okay, so I'd go to y equals, I would type in sine of x divided by x. And remember, if you're ever questioning it in this class, be in radian mode. Let's zoom trig it, zoom 7. I want the limit as I approach 0. It looks like as I get close to 0, I'm getting to 1. If you hit trace and type 0, there's actually nothing there. So what's happening is there's a hole here, but it is getting closer and closer to 1. If you look at the table, you can see that. You can see it's increasing and then decreasing. If I get a little bit closer, let's make y values, let's start at negative 0.1, and let's go by 0.01s. Look at how close to 1s they're getting. This one says 1. That's crazy. It's not really 1, it's just being rounded. But you can see as I approach 1, or as I approach 0 from either side, the y values are getting infinitely close to 1. Or at least that's what they look like. Now that was fine for us last year. We'd say, yeah, it's equal to 1. I believe it. The graph looks like it. The table looks like it. But now you're in calculus. You care more about math. Yes, you do. How can we prove that that limit has to be 1 and not 0.99999999999? Got to be 1. Well, let's see. There's a tasty little theorem called the sandwich theorem. It's also called the squeeze theorem sometimes. It says, if g of x is less than or equal to f of x, is less than or equal to h of x, for all x not equal to c in some interval around c, and the limit as x goes to c of g of x equals the limit of x goes to c of h of x, and they're both L, then the limit as x goes to c of f of x has to be L also. So that'll prove it. But how? Okay, so remember, theorems sound confusing, but they're really not all that bad. This first thing says that you've got 3 distinct functions, g of x, f of x, and h of x. And except for at the value I'm looking at, so minute ago I was looking as I was approaching 0. So let's say 0 is C. Except that the one value I'm looking at, if they're always in this order, so G is always the smallest or equal, F is the next smallest, and H is the next smallest. It looks something like this. Here's the G graph, that's the black one. You can see that's always on the bottom. Here's the H one, that's on top, the red one. That's always above all the other ones. And the F one, right in the middle, kind of gets squeezed or sandwiched right in between those two. That's why it's called squeeze sandwich theorem. At C, we don't really know what happens, but for every other value, they're in this sort of order. Okay, if that's true, you can see here, the limit as x approaches C of g of x, so the black graph, equals this value L. The red graph, the limit as x approaches C of that, is also L. So if you know that these two limits are L, and this blue graph has to be squeezed in the middle of them, does it kind of make sense that that limit has to be L also? If it's always squeezed between these two whose limits are L, it's got no other place to go. So that's what this theorem's saying. Now let's see how we can use trig to show this. Remember the good old unit circle. So unit circle, remember unit just means the radius equals 1. So here's the unit circle. I've got some angle theta, and I make a triangle out of it. It intersects the unit circle at A. And if I drop it straight down, I'm going to call this point B. So sine of theta is opposite, which is the length of AB, over hypotenuse. And this length has to be 1 because the radius is 1. So sine of theta here would just be AB. Cosine of theta would be opposite or adjacent, which is OB, over hypotenuse, which is 1. So that's just OB. And tangent of theta, I extended it a little bit and made C this point on the unit circle, straight out from O on the x-axis. And I went where that would connect with this angle. I called that D. So tangent is opposite, which is DC, over adjacent. Now that's, if I go all the way to C, that's got to be equal to 1 because that's a radius. So that's equal to DC. Okay, so I've got that. Now let's talk about areas. Remember, area of a triangle is 1/2 base times height. So the area of triangle AOB would be 1/2 the base, which is OB, times the height, which is AB. Which is the same as saying 1/2 cosine, that's OB, sine, because that's AB. You believe that so far? Well, it's true, so you should. Area of a sector we did briefly in pre-calc last year. Just believe me, that's the formula 1/2 theta r squared. We definitely did it last year. I don't care if you don't remember. So the area of this sector, AOC, so this sector, this piece of pizza there, is 1/2 theta times the radius, which is 1 squared, which is 1/2 theta. Excuse me. Finally, the area of triangle DOC. So now I'm looking at this big triangle, DOC. That's 1/2 base, which is OC, times height, which is CD. OC is 1, because that's a radius. CD was what tangent was, so that's why I have tangent here. So now look at this picture. That blue triangle is definitely the smallest, then that green sector is the next biggest area, and that red triangle is the biggest area. You can see that just from the picture. So make those substitutions. The triangle's area is less than or equal to the green sector's area, which is less than or equal to the red triangle's area. Okay? We can ditch the 1/2s, divide each piece by 1/2, get rid of that. Okay, so now I have this line. I can divide everything by sine, If I divide this first thing by sine, I just have cosine. This becomes theta over cosine. And this becomes, this is tangents. Remember, tangent's really sine over cosine. So if I divide out the sine, it becomes 1 over cosine. Don't believe me? Sine over cosine divided by sine. Complex fraction. Sine over sine cosine. 1 over cosine. Check. Now let's take the reciprocal of all of this. When you take the reciprocal of an inequality, the signs flip. Don't believe me? Look over here. 1/3 is definitely less than 1/2, which is definitely less than 2. When I take all those reciprocals, 3 is bigger than 2, and it's bigger than 1/2. So if I take the reciprocals of all of these, the signs flip. Now let's take the limit of each of these as theta goes to 0. So as theta goes to 0, 1 over cosine, plug in 0 to cosine, cosine of 0 is 1, right? Cosine of 0 is 1. So this is 1 over 1, which is just 1. The limit of, as theta goes to 0 of cosine, we just said a second ago, was 1. So this one over here is also 1. I don't know this limit in the middle, but that's what I was trying to find, and oh, what do you know? These three functions that were all in order, both have, these outer functions both have the same limit. So that means this inner function, which is the one we were trying to prove a second ago, see, right there, also has to have the same limit of 1. And that's what I said on the last page here. So by the sandwich or squeeze theorem, the limit as theta goes to 0 of sine of theta over theta equals 1. And normally we won't use thetas, we'll be using x's, but same idea. That proved without a shadow of a doubt, the limit of sine x over x is always, 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 always 1. Now, am I ever going to ask you to repeat that proof? No. Could you follow it with me explaining it? I hope so. Could you not follow it at all? That's disappointing. But you'll still be okay if you remember this fact. That's always, always, always true. That's going to be a big part of the next few days. So let's talk about some more trig rules. I just proved this one. The limit as theta goes to 0 of sine theta over theta is always equal to 1. By doing almost the same thing, I could prove that the reciprocal of that is also equal to 1. So I could also use the squeeze or sandwich theorem to prove theta over sine of theta equals 1. So that's kind of nice. It doesn't matter what order it is, what's on top, the limit's 1 in either case. So you don't even have to remember what's on top. Always going to be 1. How about cosine? Now, as theta goes to 0 for cosine of theta over 0, remember cosine of 0 isn't 0, it's 1. Right? I keep drawing this because I want to make sure you believe me. Cosine of 0 is 1. So 1 over 0 is not that indeterminate form. If I get 1 over 0, the limit doesn't exist. The other way, if I put the theta on top, cosine of theta on the bottom, as theta goes to 0, top is obviously 0, bottom's 1. This limit does exist, and it's 0, and there's nothing I really have to do to prove it other than plugging in the numbers. Okay. There's going to be some more trig limits that you're going to see in the next class. So hopefully by watching this video, you're totally caught up. You can start problem set number 17 if you want. You won't be able to do number 35 quite yet. So if you want to hold off on that, probably wouldn't be a horrible idea. So I'm not officially assigning it, but if you want to start it, you can do pretty much the whole thing.